But we're going to do the simple thing. It's just whatever this computer says, that's the one that we're going to trust. Well, that doesn't really help all the time. And that's when we get into different forms of distributed consensus. So instead of it being literally every single operation has to be going through the same person all of the time, and we have no ability to handle the absence of the person or the absence of, or just the capacity of the individual, we have distributed consensus, which give us an ability to handle going beyond the availability of just one entity, going beyond the ability of just one person. So it's not one person is in charge, and as soon as that person's gone, we got nothing. There's nobody in charge. And dealing with capacity of a single person, or both. Maybe sometimes you have an algorithm that addresses both the availability and the capacity of an individual to take care of these things. And so one of the really simple ones that we do use a lot in computing that is dealing with failover, it's dealing with availability, but not capacity. So it's still limited, we still have the bottleneck of a single computer, but we no longer have the problem if that computer goes away, we're completely screwed. And that's replication with failover. So imagine like a database where you have a complete replica. So you have one database that is the online version of the database, all of your reads and your writes happen to that database. Oh, that database is gone. For whatever reason, we have this replica that is, in a sense, a kind of distributed consensus in that we know which one is in charge right now. When that one, for some reason, goes away, we know which one is in charge next. We have consensus about who is in charge. Now, we don't have capacity ability. We still can only go as fast as the one computer. Same thing with RAID 1. RAID 1, you have multiple hard drives. All of them have the exact same image. In a sense, only one of them is being treated as the one that's in charge. With RAID, it's a little bit vague because maybe your RAID controller is in charge instead of the particular drive or something like that. It just depends on how we're talking about it. Essentially, you have one instance that is the one that we are doing the performance with. All of the operations are happening on one instance. And if one of those instances goes away, we have a clear answer for what do we do next. So that is replication with failover, which is barely distributed consensus. Barely. We have a different, yeah.
So I think RAID 1 is technically not a consensus because you have two disks, and if you write something on both disks, you usually read from just one of them. So there's no consensus when you do the read from the RAID 1. Because you simply read from one of the disks, and you don't check that the other disk has the same or different answer, actually.
So you have consensus in this case. It is the RAID controller is the one in charge.
Okay. Oh, that's right.
Yeah.
Okay.
So another form of consensus that has the opposite behavior, where you don't have availability, you don't have any notion of failover, but you do have more capacity, is sharding. And so you can think, going back to the RAID example, that's like RAID 0. You don't have any replicas going on. You don't have more than one copy of anything. But you know where the data at this location is located. It's on one particular drive. And so sharding is a similar approach. We have distributed consensus in the sense that everybody knows who's in charge of what part of the problem. So it's like distributing parts of the problem. And so we could be doing this with multiple databases. I don't know that it is as common with, to split it across different servers. I mean, depending, like if you're doing like Oracle or something, it can definitely happen. But it's very common with like certain kinds of NoSQL databases, is that you would shard based off of a key across multiple servers. And so a particular server is in charge of whatever the value is. That's a very common thing in certain kinds of NoSQL databases. DNS can be thought of as a form of sharding. You've got, theoretically, we could have all of the DNS values are stored in one place and that's where we all go. In practice, that's not what we do. In practice, each of these different servers is responsible for their chunk of the problem. But DNS, I think, is a really good example of where this becomes a problem from the perspective of distributed consensus. Is that, okay, so the different parts of the problem we know are being distributed in different servers. But the question of which servers are responsible for which parts of the problem, you have to have a central authority for that. So in a sense, you have to have the .com roots for .com or whatever, all the different DNS roots. That is your root of authority. So everything else, so we get beyond the capacity problem, but then we don't have the availability baked into DNS as simply written anyways. Like in practice, we've got good availability on DNS, but at least as described as a protocol, DNS isn't describing what would happen if you can't talk to the one .com server under the assumption there was exactly one, which there's not in reality, but pretending that there was, that's where the problem would come. And as weird as it can be to think about, failover and sharding, we can usually wrap our heads around those. The problem is when you get anywhere in between. It seems to be that anytime you have an algorithm that involves multiple parties operating in order to achieve a higher level goal, like an emergent property of an entire system that involves multiple parties behaving independently, humans seem to be really, really terrible at figuring out how that works. We're awful at that. And so that is an area where genuinely we use formal methods almost all the time. Anytime we're dealing with that stuff, formal methods are going to come up. Which brings us to this guy, Leslie. So one of the more notable figures inside of the formal methods world is this guy, Leslie Lamport, who has been a pioneer in a lot of areas of computer science, but notably, of relevance to a lot of us. He created LaTeX, which was just an extension on Muth's tech, but it was a very popular extension on top of Muth's tech. He also created TLA Plus, which we're going to get to in a little bit, which is a popular way of using using temporal logic to specify systems and to analyze behaviors of systems. But probably more notable are his contributions to the different areas, these kinds of algorithms where you're talking about multiple parties behaving independently, giving rise to an emergent combined system. And so we've got the bakery algorithm, various efforts in the realm of Byzantine fault tolerance, and of course, most relevant to today, we've got Paxos. So, a little bit of a story time. Back in the day, Leslie Lamport was trying to figure out, I think he got the feeling from looking at some of the papers that were coming out at the time, like from Liskov and Oki, that there was he didn't really feel that consensus was going to be, distributed consensus was going to be an achievable thing. By this point, we had Dijkstra's work on locks, and so we had semaphores and the result that you cannot have a purely software implementation of the lock system like a semaphore. I think there was a feeling in part of the community at that time that there was going to be something similar with this, even a looser definition than a hardline lock system. This notion of distributed consensus in general was going to be subject to similar restrictions. But as it turns out, as he was playing around with this thing and trying to create his proof to show that it was impossible, he accidentally instead came up with the example that shows that it is possible. Because I think he was trying to say, well, if there was an algorithm that implemented something like this hypothetical algorithm would behave like this, and it would do this, and this. Oh, hey, look, it happened. Okay. And so that's where Paxos came from. He was trying to make a proof that it was not possible to make an algorithm like this, and then accidentally, while he was making his proof, he actually made the algorithm. So, well, it's just kind of interesting, because then a few years later, Fisher, Lynch, and Peterson made a proof that was kind of along the lines of what I think Lamport was looking for originally, which is this idea that you cannot have both safety and liveness in an asynchronous system in the presence of failures. Even one failure will break safety and liveness. And that might sound familiar.
We'll break one of them.
What?
We'll break one of them.
Yeah, yeah. It might sound familiar, but my feeling is that there's probably a definite relationship between this property about a distributed, an algorithm based off of asynchronous communication and CAP theorem. Like it definitely seems like this is a particular case that CAP theorem is a more general version of. But this proof came out many years before CAP theorem. But the thing is, well, then why would this Paxos algorithm, which somehow achieves distributed consensus, violate this proof that they had, which is that it is impossible to have both safety and liveness in an asynchronous system in the face of failures? And the trick is, in Paxos, what we are allowing is network communication failures. And we're not allowing bad packets, we're not allowing malicious packets, we're not even allowing like malformed packets that are on accident. It's either the messages were accurately delivered or they were not delivered. And so that is under that assumption, and under the assumption that eventually a network will allow communication again. That we may lose arbitrarily many packets in the meantime, but that eventually the servers in the network will be able to communicate again. Under that assumption, then Paxos doesn't violate that, because this idea of eventual communication breaks the definition they were going with. This idea that it's, completely safe and completely live. Well, it wasn't completely live. It was temporarily dead, but that's okay. It eventually became live again. And so in that definition,
Yeah, that was one thing that when researching this, that came up, that it makes the assumption it's non-adversarial, which doesn't.
Yes, that's right. So that brings us to this one. So we were talking about Paxos so far. We're going to get into the details in a minute. But the important thing to point out here is Paxos is designed for a network where you might have packet loss, but you don't have malformed, broken data. You don't have bad data that got corrupted by some means, either intentionally or unintentionally, that could lead the entire system to some kind of incorrect result. The only thing you have is packet loss. You have network communication loss. When you have the possibility of packet corruption, intentional or unintentional, we model them largely the same way, then we are talking about what we would call Byzantine faults. The name comes from, there is a classic example of the idea of these Byzantine generals, and one of them is considered to be a traitor. And so then the question is, if everybody is, the two things that all the generals could do, they could either attack or they could retreat. And it's okay, if they all attack, then they'll succeed. And if they all retreat, then they didn't lose anybody. I mean, they would rather attack, but if they all retreated, then it's okay. The problem is if they have a mixed conclusion. If some of them attack and some of them retreat, then it is very likely that the few that did attack will be defeated. And so then the army will have lost a lot of soldiers, as opposed to if everybody attacked, then we would win, if everybody retreated, we would be okay. And so then the question is, if one of the generals, when they're communicating with each other, is a traitor, then the idea would be that that general would give different answers. I'm going to attack or I'm not going to attack to different other generals. So they would send mixed messages. And by sending these mixed messages, that would lead the entire system to one of these suboptimal states where some of them were attacking and some of them were not. In a sense, it doesn't matter if everybody is attacking or everybody isn't attacking on a certain level, as long as we're all on the same page about which of those two things we're doing. And so there are versions of distributed consensus that are able to deal with this kind of a problem. You know, again, the idea, we don't know the difference between a malicious attacker or an attack, or like just, oops, someone sent the wrong message on accident, and it doesn't matter. It's easier to just treat them all as if they were malicious and then move forward with that. And so there are algorithms for dealing with that. Leslie Lamport was a bit of a pioneer in some of that area as well. And that is the kind of algorithm that we have for blockchain, is taking some of the ideas that we have from Paxos and then moving forward with that kind of thing using Byzantine fault tolerance. But that is not the thing that we're going to talk about extensively today. So, sprinkle for the future. So Paxos itself. So we're going to start off with a bunch of terminology. So Paxos has 3 different kinds of participants in one formation of it. It is a proposer. It's a participant that is going to suggest what we should do. So whether that is, I suggest that we're all going to go to dinner at the burger place instead of the pizza place. Or I suggest that server 3 will become the new leader of the collection. Or I suggest that, you know, the thing which happened, you know, the weather yesterday was sunny, or whatever it is. The proposer is one of the participating computers, usually, that is suggesting what the thing is that we're all going to agree about. An acceptor is a participant that will help to decide whether or not we have achieved consensus. So it's one of the ones that will listen to the different proposals. It's not necessarily making a value call on these proposals. I think that's one of the problems that we think of with Paxos, is if we're coming to an agreement that we all like or something like that. In that sense, computers don't like things. You know, they just are trying to not disagree with each other. It's not important what the result is. They just are trying to come up with the same result. And so these acceptors are behaving in a very particular way that will try to achieve that goal. There's another type of participant that is often called the learner, and that is where it is neither a proposer or an acceptor. It is just listening to all of the messages so that it can figure out, have we reached consensus? So it's not contributing to the consensus, it's just trying to determine, have we reached that? It's not adding a whole lot to the algorithm itself, generally speaking, so we usually kind of throw out the learners from the conversation about it. It's worth noting that if you were to actually implement it, you might want to add learners, but from the perspective of analyzing the algorithm, we can kind of ignore them for now. They're not changing any of the behavior. Rounds. So another one of the key concepts of Paxos is this idea of a round. But the name round, I think, is a potential place where it's going to trip you up. Because it might seem like we're talking about the first thing that we're agreeing on, or the second thing we're agreeing on, or like successive values for a particular, you know, if it's like a variable, what are the values that we're assigning to that variable? You know, it's the first value we've assigned to it, the second value we've assigned to it, or it's the first decision we've made collectively, the second decision we made. That is not what these rounds are referring to. In this case, rounds are just one component inside of coming to the consensus once. And so it's a little bit hard to follow that aspect of it. I think this is the thing that trips more people up about Paxos and Praxis. You can think of it more as it is the number of person who has shouted out what we should do or what the decision is. It's kind of a way to think about it. So it's like, oh, we were talking about like the third option someone proposed, but I think we're going to go with the fourth option we should propose. In this case, the third versus fourth options would be the rounds. Okay. So it's a little bit hard to follow. It doesn't really feel, why are we calling that rounds? That's just what they call it in this particular case. Again, like I said, rounds are not helping us to get to the second thing we're making a conclusion about. Rounds are the different sets of attempts to try to come to a conclusion about the first thing. So now we have a round identifier. Now, I'm calling it a round identifier. Most of the time people just say, well, it's the first round or the second round or the third round. They use it integers, they use a number. I think once we're getting into the realm of formal methods, we should be a little bit more specific than that, because the thing is, it's really important that two different proposers are not ever going to be able to pick the same number. They can't pick the same number. It's like, okay, well then, how did you decide that? And it's like, well, you know, we guarantee that they have different integers. Like, gee whiz, that sounds like you also had a distributed consensus algorithm beforehand. Like, so I'm gonna put in a separate thing and just say that it is some kind of a value which has a total order. So that just means if you're given any two round identifiers, that one of them is bigger than the other one. One of them is greater than the other one. Whatever that means, you know, if we're talking about like, you know, we're all programmers in here, so if you had like a thing where you've got a comparator, and so you've got, you know, that doesn't necessarily mean that they're both integers. One of them could be like a class, and it has an integer and it has a color. And so somehow when you compare the classes that have integer and color, one of them is greater than the other one. Maybe like the blue one is greater than the green one, but then if they're both green, then the numbers are more important, or whatever. Whatever your compound comparison operation is going to be, doesn't really matter, as long as you have one. And that's the key here for round identifiers. Somehow you have to know that no two instances in the network are going to ever pick the same number. Because if they do, all bets are off. And so a really easy way to fix that is to put, you know, have it be a compound, like a number, and then my identifier. And some people do that by putting a decimal point, which just bothers me, because what happens if you have more than 10? You know, like, it's just a silly thing that would have been really easy to avoid. And it's like, well, it's not a problem if you have more than 10, because then it would be 1, 0 instead of .1. And it's like, that sounds like the beginning of a terrible accident when someone just tried to implement that. Like, no thank you. We're just gonna say that it is sometimes you get a thing, which is the name for your round, they're comparable, and there's no way that you could possibly have two different things pick the same number. That's it. Maybe you did it with an integer and a point, and you somehow decided that you've done the decimal in a way that that's not gonna be a problem. I don't know, whatever you did, it's two things that can always be compared, and there's no way that two different servers in the same network could have picked the same number. That's all that matters. However you did that, that's all that matters. So now, the consensus value. So consensus value is, you know, in a sense, the thing that we picked. If we're picking, like, are we going to get pizzas or burgers? It's the decision, we did pizzas, or the decision, we did burgers. If it's you know, who's the leader? It's like, okay, leader 1, or leader's the server 1, or leader's server 2, leader's server 3, whatever that's going to be. It is the conclusion that we have all come to a consensus about. That's what I'm calling the consensus value here. Okay? So in a sense, Paxos is all about trying to come to a consensus about a specific value. That's what we're trying to do. So now we have 4 different types of messages in this Paxos algorithm. We've got prepare and promise, and then accept and accepted. These two are kind of paired together. Prepare and promise are the messages that happen during the first phase, which we'll get to that in a second. And then accept and accepted are the messages that come together in the second phase. So a prepare message is going to be coming from a proposer. A promise message is coming from an acceptor. An accept message is coming from a proposer. An accepted message is coming from a acceptor. A little bit tedious, but in a sense you can just think of it as there's 2 different sections, which we'll get to that actually. The 2 different phases. You get your preparation phase, you got your acceptance phase. So in the preparation phase, you've got your proposer is sending out a prepare, and the acceptor is going to respond to your prepare message with a promise. And then in your acceptance phase, your proposer is sending out an accept, and then the acceptors are responding with an accepted. That's usually the terminology that they use for this kind of thing. And the preparation phase comes first, and the acceptance phase comes second.
And across all these, there's a vote, and it can be rejected or not reach majority or something.
Yeah, and we'll get to that in a second. So it's a lot of tedious stuff, but we'll get to that in a second. So majority. On the one hand, majority seems like a concept probably a lot of people are familiar with, but it's important, the nuances of it's very important how that happens here. So a majority is more than half of the acceptors. That's the majority. And so that is the key that makes Paxos work, is that when you're dealing with 2 different majorities, they may have a whole bunch of different servers. They might be mostly not the same servers. As weird as that sounds, you can have 2 different majorities that are mostly not the same servers. But what you can't have is 2 different majorities that are entirely not the same servers. You're going to have an overlap. There's no way you can have 2 different majorities that don't overlap. That's impossible. And that's the point. It's because of the pigeonhole principle. You cannot have 51% of the acceptors and a different 51% of the acceptors where none of the acceptors are the same people, unless the collection of acceptors is completely changed, in which case, well, all bets are off at that point. You cannot have 2 different 51% of the acceptors where there are no acceptors in common. You cannot have it. So that's why the important thing with the majority is we know that at least some of the majority from one set is the same that we're in the majority from a different set. And that's the key. That's what makes Paxos work. So now let's actually get into the algorithm. So when you start, the whole thing is starting when you have a proposer creates this that round identifier. Remember that we said, it's like a number, maybe something to do with the identifier of the proposer, whatever it's going to be, doesn't matter. It just picks a value. Just pick something. It doesn't matter what the number is, as long as it's comparable, as long as we compare it to everybody else's. You just pick a number. Okay. After you pick that number, you create this prepare message. It's just saying, hey, I think this is what the round number should be. That's it. It's just like, here's my round identifier, round number, whatever. This is the name of the round. I think this is what the next round should be. And so that is the only thing that the prepare message does. It just sends that out to all the acceptors, or as many acceptors as it can find, whatever. And then, at some point later on, we'll get to this in a second, the proposer that sent out that message, hey, I think everybody should agree that this is the round that we're on. It's gonna get responses back from these acceptors about whether or not it agreed with that idea. And it got promise messages coming back from these acceptors. And the promise message, we'll get to that in a second, but one of the things the promise message is just saying whether that is whether they agree that yes, we're on this round that you just said. If it gets a majority of the acceptors sent back these messages that said, yep, that's the next one we're gonna be doing, then we're able to move on to the next phase, the proposer is able to. So this is the only thing that the proposer knows, is it made up this identifier, this number, whatever, it sent it to everybody, and then it just knows whether or not it got a majority response or it did not. That's it. So now we move on to the acceptors. So the acceptor is just sitting there hanging out, it doesn't know what's going on, and all of a sudden it sees this prepare message. And now it knows, oh, we must be in the beginning of the preparation phase. And so if this round identifier, which it just got, the round number, whatever you're gonna call that, if the round that it just said is the biggest one it's seen, like, oh, the random number that he picked, that's bigger than all the other random numbers I've seen, then it will create this promise message that says, yep, here you go, I agree, that's the next round. If that's just the biggest round number it's seen, I agree, that must be the next round. But here's the twist. If the acceptor has ever sent an accepted message, which we'll get to that in a second, if it's ever sent one of the messages from the second phase before, then in that promise message it sent back to that proposer, it's going to include a copy of the accept message that it sent out previously. Okay, and so either it's sending back the promise message, which is just saying, yep, you got the latest round, and I've never sent an accepted message before, we're good to go. Or it has sent an accepted message ever, in which case it's like, oh, okay, you've got the next round, but I've already accepted this previous one. So that is the behavior of the acceptor inside of the preparation phase. And so this one's pretty simple. It just gets a thing came in and it sends a response. Yes.
So it tells it whether or not it's still, if it's a bigger number, it still tells the proposer that.
Yeah, if it was the biggest number it's ever seen, then it will send this message.
Okay.
Yeah. So now we're moving on to the second phase, this acceptance phase. So if we're here, that's because the proposer got back from these acceptors all of these promise messages. Promise messages might have just been, yeah, I like your round number. Or it was like, I like your round number, but I sent this accept message before. That's the only two things it could have gotten back. But if we're in this phase, that means that the proposer got back enough of these promise messages that it knows that it's got a majority and it can move forward. So now we know we have a majority and everybody's on the same page. We like your round number that you picked. That's the biggest number we've ever seen. So now it has to do this analysis. It has to decide what is the consensus value I'm going to put in. Now, this is where it starts to feel a little bit different than humans. Because with humans, when we're trying to decide if we're going to go get pizza or burgers, if we're trying to decide, who's the leader or whatever, you got a preference for these things. Like that was the whole point. That's why you started this conversation. And in Paxos, you might not get a choice. That's the weird thing. Just because you're the person who's now in charge of coordinating and we're sending the messages out and everything, doesn't necessarily mean that you get the choice. Because as it turns out, if none of those promise messages that you got back, so you're the proposer, none of the promise messages you got back have any of those accept messages attached to it. You got a promise and an accept, or just a promise. So if it's just a promise, you're good to go. You can pick whatever value you want. Okay, we're doing pizza. Oh, we're doing burgers. Doesn't matter. But if even one of them came back and it says, okay, I like your round number, but on a previous round, I thought we agreed that we were doing pizzas. Well, now the proposer is stuck. They have to do pizzas. They don't get to choose anymore. Their choice is over. Unless there was another one that was even later, which said that it was burgers. Oh, okay, then we're definitely doing burgers. But that's the point, is that if the proposer got any responses back that had any accept messages in it, they no longer get a choice. They're going to be stuck with picking whichever the latest number they saw. Whatever choice was associated with that, that's the one they have to choose now. And once they made that choice, they figured out, like, either I got to make my own choice, or nope, someone said that we already had an accepted answer, and so I'm stuck picking whatever the latest accepted answer was. So once we have figured out whatever that value is.
A previous one that had a consensus, you mean?
Yeah, we saw an accept. If any of those acceptors said, like, yeah, you've got the latest round number, but also on a previous round I said that we were doing pizzas or burgers.
So this, because some other ones goes like this one, go the promises and say,
Yeah.
it's gonna be pizza.
In other words, they thought there was a consensus, or it just observed a consensus and sent out this message.
Mm-hmm. Yeah. And so if the acceptor thinks that at some point in the past we had critical mass and then we agreed that it was pizzas, or we agreed it was burgers. And that's the thing, is it's not necessarily the case that all the messages it got back even agrees. Some of them might say that pizzas, and some of them might say burgers.
But I thought it saw an actual majority.
Yeah, even though they both thought they had a majority, they might have two different values here. But that's okay, because what will happen is, whichever one is later is the one you go with. So, now that you've got whatever your choice, either you were the first one ever, and so you get to make your own choice, or you were not the first one ever, and so you're stuck with whatever the most recent person who made a choice was. Now that you have figured out what your value is, you create this accept message. And your accept message is the round number, the round identifier that everybody had promised for you. Because remember, we're only here because we think we had a majority of all of these acceptors who said, yeah, we like the round number that you came up with. So we're only in this spot because you had the majority. So now you're creating these accept message with your round identifier, your round number, and then whatever choice you are stuck with. So either the one that someone else had made, and now you're stuck with it, or no one else had made one, so then you get to pick. So that is what you put into your accept message, and you send that out to all the acceptors. So that is the proposer's last thing that they're doing in this algorithm. So now the acceptors. The acceptors have just received an accept message. So if no promises have been sent for an even bigger round number, so that's the thing to keep in mind, like, more of these proposers could have been coming in while we're waiting on this accept message. And so these other proposers may have had an even bigger round number. But if nobody has done that, you've just got an accept message for the biggest round number you promised, then you will accept whatever value they had and send it back and say, yeah, this is an accepted message. And so your accepted message now includes whatever value that was, and then whatever the round number was. And you keep that accepted message around in case more people show up with promises. And then you would include that accept message, which is the value that we accepted here, and whatever that round number was, and then you're sending that from now on. Yeah.
If you're an acceptor, you did not have to previously send a promise to accept the acceptance from that proposer, right?
You did.
You did. So
Yeah.
you can only accept if you previously sent a promise for that same value.
Not for that value. You just have to have. It has to be the largest one that you have seen. So that's the trick. Is maybe you were out. Maybe you were an acceptor who was out of commission while the previous promises were going out. Well, again, we are assuming non-Byzantine fault. We're assuming that everybody is behaving in good faith. We're not having weird, bad packets. So every packet you see is legit. So based off of that, if you ever see coming into you a message that says, hey, this is an accept, here is my round number, and that round number is bigger than any of the promises you've ever seen, then yeah, you're gonna take that as an accept.
So if you come online for the first time, the very first packet you sent could be an accepted.
Yeah, potentially, yeah.
Cool. Nice.
So you could have missed the previous vote before you see one that's bigger than anything you've seen before.
Yep.
You go with that.
Exactly. Yep. So that is the behavior of the acceptor. And so once you have a majority of acceptors have sent an accept message for the same consensus value, then you've got your consensus. And that's one of those weird things. Well, what happens if you're if they're not even the same round numbers? Like what happens if the round identifiers are different? Well, it doesn't matter, because at this point, in a sense, just recall that the whole point of this was to come up with a consensus around a particular value. And so once you have seen that a majority of the acceptors have accepted, for whatever round number it was, the same value, you're already done. So it's kind of a weird algorithm. One detail that we kind of glossed over is, well, what if somebody sends you messages and that is not the biggest round number you've ever seen?
And that's when you have instability, you know, like you have some number you're gonna eventually arrive to the right number.
Well, it's, yeah, the question is just what is the behavior when you see one?
Okay.
And the answer is, the algorithm itself doesn't say that you have to do anything. You could just drop those packets. Like, if an acceptor sees a promise, or sees a repair come in, or an accept come in, and that wasn't even the most recent number that it had seen, you just ignore those.
You ignore anything but the latest.
Yeah, you ignore anything but the latest. But if you do that, the algorithm is going to run a little bit slower, because then you can't tell the difference between like actual packet loss and like you're just not responding, because like, well, that's not the latest one I've seen, so I'm just not even going to talk to you. Like, well, then how big was the thing you saw, or whatever? Like, is it ever going to tell you, or whatever? And so in practice, it makes it go a lot faster if you do send a negative message. So if the algorithm doesn't require it, it will work even if you just drop the packets. But in practice, it'll go faster if you send back like, no, that's not the biggest number I've seen. You could say the biggest number you've seen, or you could just leave them guessing. But even if you just say, well, that's not the biggest number I've seen, in practice, the algorithm will move significantly faster, because now you're not waiting for a timeout. Like, you're like, okay, well, I don't need to wait for another message from that box. Like, I can just move on. So now we've got, so that's largely, we've been talking about the happy path, so that now it's like the sad path. What are the different failure modes? And that's the trick. That's what makes Paxos work better than everything else is for that kind of a thing. Is that it has behavior that's well defined in the SAT path as well. So, is there anything else I put in there? Yeah, failures can happen at any time, but the implications of failures at specific points in time are different. So if the proposer fails during preparation, so it's like it sent the messages out, oh, now the computer crashed. Like it just sent the preparer. It picked a number, it sent the preparer messages, and then the server crashed. Okay, well, what's it gonna do? Well, the thing is, I mean, it's not just that. It's even like multiple proposers can be proposing things at the same time and stomping on each other. That's another one of these failure modes. But the thing is, like, the algorithm will handle that in the fullness of time, I suppose is what you would say. Is that it is a real danger that if two of them are like constantly going after each other, like, oh, I picked a bigger number, and then it sent promises out first, and then the second one comes in and they're like, well, I picked an even bigger number, and it sent promises out, and so then the first one thinks it has, you know, a majority now, and so then it sent out its accept messages, but the accept messages were all dismissed because that second one had come in there with an even bigger round number and beat them to the punch, and so now all the acceptors are waiting for that one to respond. But before that second one has a chance to send its accept messages, the first server now gets its act together, like, okay, well, I'm gonna pick an even bigger number, and it sends its things out, and then, so you can be in this live lock situation where each one of them is one-upping each other before you can ever get to the accept messages. And that is one of the modes that Paxos can live lock on, so.
The failure mode is when they get a different majority keeps coming back, or did I misunderstand?
No, so they're getting legitimate majority backs for promises. So, like the first one sends, let's say I'm you know, round number 1. Hey everybody, I'm round number 1.
Mm-hmm.
And so the acceptors all hear that, like, oh, okay, and they get their promises back, and so the first proposer now has a majority for promise 1.
Mm-hmm.
And it takes just a little bit too long to make its accept message, because proposer 2 sends out, well, I'm sending out round 2, and it sends those messages out to all the servers, and all the servers are like, well, 2 is an even bigger number than 1, so yeah, round 2, that's the one we're going to use now. And okay, and so now proposer 2 then is the one taking its time trying to prepare its accept message, and then proposer 1 sent the accept message. Oh, the accept message failed because it wasn't
So the
round 1
here
anymore.
is different proposals, keep sending out proposals and then flaking out.
Yeah, they keep, you know, in a sense, if they're taking too long between getting their responses and sending their accept message, then that will potentially allow these two proposers to keep making bigger and bigger round numbers, and then nobody wins. And so that is one of the things you have to watch out for in Paxos. That's one of the things that can happen. Another failure mode, an acceptor could fail during the preparation, but that's the thing is, like, as long as the majority of them fail, as long as the majority of them are working, then it doesn't matter. So if you got one of the acceptors, just the server goes down. As we were talking about earlier, like, it didn't never see the promise, but it eventually gets the accept message. Well, it will accept it if the round number on the accept message is later than any ones it had ever seen. And so it's able to handle a failure mode at that time. And the only thing that will keep, you know, the algorithm continuing to proceed is, as long as we've got the majority of them still responding, then we're good.
Question?
Yeah.
Is the majority then defined as n-1 since that?
No, it's still in, and that's important. We'll get to that in a little bit. Yeah, it's still, even if they're not all responding, the numbers here don't change, and that's important. That's a good call out there. So another possible failure mode is that the proposer fails after preparation. So the proposer got its majority back, like so proposer one
Oh, yeah.
sent out, like, oh, we're doing round one. And everybody was like, yeah, round one, that sounds great, let's do round one. And it got its messages back, and promptly right before it was about to send its accept message, it died. Well, as long as another proposer jumps in.
I thought that's the one we were just talking about, right?
It's similar, in this case, instead of them trying to race, it's one of them died after it got permission. And so then the idea is,
The later ones are proposed anyway.
as long as there is, and that's the assumption we have to add. So in the first one, we had the problem of, well, what happens if we have too many and they're racing each other? Well, that is a concern, and it's something that might not be able to be fixed. In this case, we have a different problem. What if we tried to solve this problem of like two different proposers racing against each other with this idea that, well, okay, we're just gonna have one proposer and that solves the problem. It's like, well, no, because then what happens if the one proposer dies and never comes back? Like, no, that's not okay. So you have to have more than one proposer. Like,
Right, that reduces this, whatever, single source of truth problem.
yeah, exactly. So another possible failure mode is the proposer fails during the acceptance mode. So the proposer said, okay, we're gonna do round one. Everyone's like, okay, we're good, round one, we're all on the same page. And the proposer's like, okay, in round one, I'm saying we're gonna go to eat pizzas. Okay, and I told everybody that. And before anybody could come back and tell me, yeah, pizzas, that sounds great, we're all on the same page. Proposer done. Like, it never hears any of those messages again. Well, and that's the thing, is like, none of those acceptors necessarily knows that that's what we have agreed on yet. Like, maybe it was the only one that heard that message, and so then everybody else got the burgers message instead, so none of the acceptors knows. And so, okay, well, how do we handle that? Well, that's the trick. It's those promises, those successive promises that are being sent. So if another proposer comes in and sends another, well, we're gonna start round two now. It's like, well, the first guy got all the way through saying pizzas. So even if proposer two is like, all right, we're doing round two. Okay, everyone's like, yeah, we're doing round two, but just so you know, we already agreed in round one that pizzas are what we're doing. And it's like, oh, okay, so now proposer two is like, okay, round two, apparently we're doing pizzas. And that's basically.
In memory of round one, we're gonna do pizzas.
In memory of round one, we're doing pizzas. Yeah, exactly. And so now we've got an acceptor failure during acceptance. Kind of like with the promise, with the preparations section. As long as it's just like one or two of them or whatever, it's okay. If we still have a majority of acceptors around, we're okay. If we lose a majority, we're screwed.
You said the idea is like they're always going to get the messages eventually. So like, if an acceptor goes down and it comes back up, does it get like all the history, even if it's a bunch of stuff that happened in the past, or?
It may not get all of them. It just needs to get enough of the information, and so it would be from the proposers and stuff like that. But that's the trick when we say that eventual messages. That's why the Paxos one is generally seen as not an impossible reality. Is it's not saying that every single server will eventually come back. Maybe some of the servers never come back. It's that eventually you will have a majority capable, a majority number of acceptors around talking again at some point in the future.
Whatever nodes are online, we'll see.
Yeah, you will eventually have enough servers again.
And if they come back, they might just see like some number of old messages. They won't necessarily see every single thing they missed.
Yeah,
probably,
maybe not.
okay.
Yeah.
Does each proposer know the size of the network? Do they
Yes.
know N? Okay.
Every proposer and every, theoretically.
Every single node is
It's
inside
a
of
source
it.
of truth on the network side.
So what you're saying,
Yes,
probably.
we have to have that established up front, yeah.
Okay, you have 10 computers, no matter what, even if there's just 3 of them, or whatever.
Uh-huh.
You always have that total N computers, no, that doesn't change.
That's right.
Is there a way of proposing that there are now only 95 computers in the network?
It doesn't-
Yeah, it doesn't allow
That's-
additional.
Doesn't matter, you know?
That's a very good question, and we'll get to that in a second.
Yeah.
If you
That's
can
like
die and
this,
never come back up, what happens when it's n divided by 2 is
That
4
is a-
plus 1?
That's the
That's the
paradoxal.
Yeah. Yeah.
Different
That's anti-Paxos, the other island, so.
Oh.
I mean, it doesn't allow nodes added.
What?
It doesn't allow nodes to be added.
Not added or deleted, yeah.
Just go.
I mean, I guess theoretically you could replace them, and then that would be the equivalent of like all
So you
packets
can
have
put
been
new
lost.
ones on to
but-
like replace old ones.
Yeah, but that's.
You can
that's-
agree on the consensus of how many you're gonna have, once you get that, then you can change.
Exactly.
Wait,
So, and so here's this interesting thing, what kind of emerges from this is that there are 3 different points of no return in the Paxos algorithm. The first one is that a new minimum value is established for the round identifier. Once we have a round identifier, and we've got, you know, promises for that, the number will never be smaller again, never again. There's no going back.
That's funny.
So that's the first one. The second one, which is weird, is that the eventual consensus value has been established as a point of no return that happens before we reach consensus. In a sense, I'm not saying that we know the answer. I'm just saying that mathematically, an answer exists. What eventual consensus value it will eventually be is actually established earlier on than the point at which we actually reach consensus. Because something about the way that these messages have happened, we actually will have an answer before we know what the answer is. It's kind of,
Well,
yeah.
Established means a majority has accepted that minimum value.
Yes, yeah. A new minimum value is established for the round identifier. In a sense, that then becomes true from then on. In temporal logic standpoints, we would say that that is eventually always true. It is eventually always true that the round identifier that is acceptable is not lower than this value. And then eventually always true that it will not be lower than this value. And eventually always true it will not be lower than this value. Yeah.
But is that point when a majority of acceptors have accepted that minimum value?
Just the promises, yeah. This one happens when we get a majority of promises.
Promises.
Yeah.
So it need not be all of the acceptors, only like a majority.
Only a majority, yep. And it's the same thing with this one, is once we have a majority that have, once a majority have sent accept messages, or I think it's actually slightly before that, and that's the weird aspect of it, but we would have to get into the nuances of it. But, yeah.
Well, wouldn't it be weirder if the order of those is swapped? You get consensus and then you figure out what the value is?
No, I mean, because that more closely relates to human ones. Is when you have decided that we have consensus, like, in a sense, they tend to go hand in hand, but it is in fact the other order, usually with human-based algorithms.
Well, it sounds like you first figure out the choice that is acceptable with 51%, and then the other 49 pick it up, and then that's when you get your consensus, right?
No, it is the 51% that gets us to consensus.
Oh, okay, so
Yeah.
So the consensus occurs after 51% state same value.
Yeah.
And then get the 49 after the second round.
Yeah. So, the minimum round one, as we said, is just once a minimum round identifier has been established by a majority of acceptors, round identifier can never decrease. We can represent this in temporal logic, and in fact we do.
What happens when it goes above Graham's number?
Or just
Or
larger
max
than the whatever
yeah.
value
It's
you
over
store it in.
max
It's
int,
like-
yeah.
Yeah, max int or max whatever data store you put it in, like, yeah.
Max long.
Yeah.
So they
Um,
divide by 0.
The decision is finalized, so there's a specific point in the process at which the final consensus value will become set in stone even before consensus is fully established. So it's like not everybody is on the same page that we have consensus yet, and yet it is no longer possible for that value to change just because of the nature enough of the people have seen those messages. Now it couldn't change. Weird, but it is a property that you can prove is true. And then it seems weird that I'm saying that consensus achieved is also a point of no return. So it's like, well, you know, why would that be a point of no return? That wasn't the whole goal. As long as that was in fact your goal, because you know, why would we say that this is a point of no return, and then we move on to the next? It's because Paxos is one and done. You only get to come up to consensus about one thing ever. That's the weird thing about Paxos. All of this stuff, all of these servers, all these rounds, all this whole algorithm, the whole thing, you come up with one decision. You can't say like, oh, we did Paxos and we've decided that we're gonna do pizzas instead of burgers tonight. So now we'll do it again and do it for tomorrow or whatever. Nope, the Paxos algorithm works one time. That's it. You throw it all away, you start over with brand new servers. That is how Paxos works. And so it's like, what? That's not even a real thing.
It's like a building consensus is really hard.
Yeah.
So.
Yeah, and then I guess with Paxos, it's HR goal.
Yeah, the Paxos algorithm is defined in a way that says once you have come to conclusion, it's over. There's not even a mechanism for starting it again.
It's not my area as much, but maybe if you have some very key cybersecurity stuff that might be useful for that, or like,
well,
you have like key identifiers throughout a system.
Well,
the agreement
potentially, but the trick here is Paxos is a thing. As weird and complicated as it seems, it is a thing that we can make really good proofs about, and from there, now we can use that to build something else. This was going to be a lot more, but we were running out of time anyway, so that's okay. TLA Plus, like I said, is a tool that Lamport made, and it is helpful for being able to analyze things like this. You can get it from a variety of different places. There's the new TLA Plus Foundation website. You can get a copy of it from there. If you just Google TLA Plus, you'll find it pretty quick. TLA Learning Resources. This is the book by Leslie Lamport, so that's nice for whatever that's worth. Most people instead suggest this one by Hillel Wayne. This one's a bit more practical, especially for like working software engineers. If you're just getting used to how would I use some of these kinds of tools for a real world problem, like in your day job or something, this is really the book that you would want for that. This is a newer book. I think this is a guy I met before. And it's a little bit more trying to explain some of the fundamental ideas in addition to doing TLA Plus, and just trying to use temporal logic more in general and showing how to use it. You got a lot more math going on in this one than the other two, but it's a good one as well. And there's a bunch of videos and stuff. Leslie Lamport, as I mentioned earlier, he's a very good speaker. Sometimes the books are a little harder to follow. Sometimes his papers are a little bit harder to follow. But I think as like an interpersonal speaker or whatever, whenever he's giving like a talk or something, it's usually pretty easy to follow. So TLA Plus is fantastic for finding bugs. I have used TLA Plus. It's the only time I've actually done formal method stuff in my day job was using TLA Plus to analyze a data structure at a previous company, and we found a really nasty bug inside of my C code. It was extremely hard to tell, and it wasn't an off by 1, it was an off by 2 problem. So it was we had a memory pool and a data structures of a particular shape, and we were trying to make a proof about the behavior of the entire system, an emergent behavior of the entire system when we had this system, and we were reusing this data pool for the data structures were all the same shape and everything, but we were constantly having them come in and being destroyed by different threads. And so the problem was 2 before we were full, it had a weird behavior where it would start, like, it would reset some of the counters and such, and so then it would like start corrupting everything. We didn't know which ones were acceptable to start overriding or not anymore. And it was because of some really weird, complicated behavior that we were getting. But with TLA Plus, not only did we find the problem, we realized that the problem came because we thought we were being clever. That's just, don't ever be clever, that's a bad idea. We thought we were being clever, and TLA Plus pointed out an algorithm, a slight modification of the algorithm that would be way faster. And so it's a great tool for that kind of stuff. And so it will absolutely find bugs if you implement something into TLA Plus. And it's got like a model checker, and that's what's usually finding the bugs. And unsurprisingly, given that Lamport and TLA Plus was in part created as a way to make things like Paxos easier to understand, there is an officially maintained example of Paxos in TLA Plus, so you can go and look at the exact details of how it works, and play around with it and see if you want to change something about it or whatever. Okay. Oh, we good? Okay. So Paxos, of course, seems like a toy now that we pointed out that you can only use it once. You've got a whole cluster of servers, a really expensive thing, and then you're literally, you use it one time and then you throw them all away. And that's just like, well, that's dumb. Like, that is never a thing that would happen in the real world. Why are you even talking about this? As I said, it's partly because we can make formalisms about that, and from there, whatever we say about that will probably help us design an algorithm that is a little more practical. And before you get into the most obvious temptation, which is that, well, we're just gonna run Paxos on the same servers over and over again, it will be fine. I'm sure nothing's gonna go wrong. I mean, maybe you'll be lucky, but again, as we pointed out, like, something about humans thinking about multiple systems that can independently operate, working collectively to come up with an emergent property, doesn't work very well. Humans just don't seem to be very good at doing those things. And repeated Paxos, where you're just using the same servers over and over again to come up with this stuff, is one of those areas that seems to be very fraught. The way people happen to implement a repeated version of Paxos by just like, I don't know, looks good to me, ship it, you know, like, it tends to go sideways. Which is why we now have these more complex algorithms called multi-Paxos. And so multi-Paxos is not like one algorithm, there are a lot of, so there's only one Paxos, but there are a lot of different variants of multi-Paxos. Constantly, all the way to today, we are still, every time you get a big formal methods conference, every time you get a big, you know, conference related to distributed systems, parallelism, anything like that, you're going to have brand new implementations of multi-Paxos being introduced that are really, really good in one super specific circumstance that you probably had never even thought of before. Why would anybody ever run into that particular combination of circumstances? And yet somebody did, and now we have a brand new multi-Paxos algorithm, which is really good for that super specific circumstances. And that tends to be what happens with these multi-Paxos. In order to get it so that you can do Paxos multiple times, you know, there's a lot of ways to do that, but in order to get good performance, you have to adjust it a little bit. And so that's the thing, it's like these different versions of multi-Paxos have different trade-offs. Sometimes you'll have a version of multi-Paxos which someone spent just an unbelievable amount of time, and it's because it works like 1% faster on this very specific type of processor versus this other type of processor. And so they have a whole PhD that the only thing they worked on the whole time is trying to make it run slightly faster On the Xeon E5400, even though it runs 20% slower than on the E5700, but that's okay because it runs faster on this one processor, and we have a proof of that, and like, we're great, good to go. And it's like, you know, they get really nuanced, which ones you would use under which circumstance. Some of them are more broadly applicable, but some of them are super niche when you would need to use them. And they all tend, they vary with just how much more complicated they are. Some of them are incredibly complicated. Some of them are just slight tweaks on top of regular Paxos in a repeated mode. So it depends on which one you're looking at, what pros and cons you're gonna have. Which brings us to Raft. So as an answer to this issue of multi-Paxos, you have all the different ones, and you don't know which one you're supposed to use, and it's kind of complicated if you wanted to implement it. Raft was an attempt to make one where the goal was to have an algorithm, which is like a multi-Paxos style algorithm, where you have a log. That we have new terminology, which we tend to have for multi-Paxos brands. A log is what your collection of successive consensus values are, is the log. And so Raft is based around the log. That's like a joke. It's a collection of logs and stuff. But basically it is this algorithm that's intended to be, you know, easy to wrap your head around. And so therefore easy for a developer to make an implementation of. That was like the goal. And it's underused. It's used all over the place. It's underneath Kubernetes. It's underneath Vault. It is being actively used all over the place. And now for my soapbox about Raft. So the thing is, so Raft has a formal proof, just like all the different multi-Paxos, just like regular Paxos. It has a proof. It's a nice proof. It works perfectly well. Problem is, in the world of Raft, the normal behavior that people do is they go and they look at Raft, they're like, that's cool, I'm gonna go write that in JavaScript, in Python. I'm gonna get a copy of this and I'm gonna go write my own version of it. The thing is, when we're talking about formal method stuff, there's another approach that we tend to take, which is called extraction. It's kind of related to the weakest precondition stuff we talked about last month, where we were saying correct by construction. If you specify something well enough, you don't have to make the code. The code can just spit out of the proof. And then you won't have any bugs, except to the extent that there was a bug in the proof translation stuff, but that's easier to wrap your head around. It's easier to see if that was something wrong. Trying to make a proof about a piece of code you already wrote, that is no fun. That is a huge effort, and most of the time you just don't have the skills to do it. If you were tempted to do that in the first place, you don't have the skills to do it. It's one of those like, and so you're in this weird spot where people just keep writing their own versions of Raft when, well, okay, you could extract the implementation of Raft. Like, you absolutely could. We've got all the proof that you would need to do it. You would be able to generate from the proof of Raft all the stuff that you would need to make an implementation in JavaScript, and Go, and Python, whatever. You don't have to have someone write it by hand and then put it under etcd and Kubernetes and be surprised when it breaks and then like what are we gonna do? Like, it didn't need to be like that in the first place. But that kind of gets us to, well, yeah, but if we're questioning, like if we're at the point where we are talking about this code extraction instead for Raft, instead of having to write it by hand, then the whole point of like Raft being simpler, and that makes it okay, like because it's simpler, so that humans can write it, but we could have just extracted it in the first place. It's like, well, if you're gonna extract your implementation from Raft, then why did you need it to be simpler? We already had the proof. We could have gotten an extracted version of a multi-Paxos that works well for your problem.
So you would extract it from TLA blocks, or from what would you?
Yeah, there's implementations of Raft in TLA.
There's extracted from, whatever, an extracted version of multi-Paxos.
Oh yeah, almost, and that's the thing is, the default we would do in multi-Paxos world. It's just because the multi-Paxos stuff is very popular in the formal methods world. We're always doing that stuff. Raft, we've got the same thing. You can extract an implementation of Raft from the code, from the proof as well. You can totally do it.
But when you say you can totally do it, I mean, is it just a compiler?
Yeah, I mean, it's a little bit nuanced. It's not something you're going to get a Go developer off the street to do it, but it's something that someone who is dealing with the formal method stuff on a regular basis, the people who are making Raft, the people who are making multi-Paxos, are definitely going to be capable of doing that because it's a common enough thing they deal with. But that's the trick though, is that you could extract an implementation of Raft from the proof, but then why wouldn't you do that? Because you could probably get a slightly better Paxos for your use case and extract that. And that's, to me, the trick. It's like, I bet there's a better multi-Paxos for Kubernetes in a particular circumstance than Raft. Like, Raft is nice, but there's probably a multi-Paxos that has a much better performance characteristic for a particular set of problems that you're dealing with. Because there's a gazillion different multi-Paxos, and some of them are gonna be super awesome for whatever it is that you're doing. Like, there's plenty of terrible choices that you would be worse off with than going with Raft, but like, there's probably one that's really awesome for whatever it is you're doing. So now I think that's, to me, the thing is like, we should be teaching Raft in colleges. We should be telling people Raft is the default thing you should do at your company if you don't know. If you have a problem that looks like, hey, we need like a consensus thing, I guess we're gonna have to go and implement this somehow, I guess ourselves or something, I don't know. Like, it would be better if you could code extract it, but even if you can't code extract it, either way, can or can't, for your small little company where you will have limited resources, Raft is probably the right answer. When we're talking about Kubernetes, when we're talking about Vault, like this thing used by a lot of people, and we have a whole lot of knowledge, foreknowledge about the way that that system is going to behave in the real world, we can probably make a better choice that's like super optimized for that. And that's the thing that gets me with this. We'll always use Raft. Raft is great. I don't have a problem with Raft. I think I'm worried about how we're using Raft. Like the one hammer that we're gonna put all these screws in the wall. Yeah.
You know if they're using the same Go library? They're both written in Go, right?
For etcd versus
etcd and
console. I don't know for sure. I think they're using different implementations of it. And I don't know for sure. I thought etcd's, I don't know for sure on this one. I thought etcd's was using a C one instead of, I don't know that for sure though.
That would be the Unixy thing to do.
Yeah. Well, I mean, when performance is important enough, then you'll use C, as we're finding out recently. That's a hot take. Too soon,
Yeah.
I think. But yeah.
I see TLA and Go, so.
Okay. Yep.
ETC.
For etcd, well, maybe they're extracting it from TLA plus then.
That'd be cool.
It could be.
Sorry, is it a hot take that you use C when you need to optimize like underlying
For performance,
GPU
yeah.
performance?
That is
That's common sense.
The
No.
workstations will read at you
There's
and they
a-
point out that they got a 17.
There's a
17
very spicy conversation happening right now in the Ubuntu world, where their plan was to go and replace all of core utils with Rust.
Yeah.
And they're discovering that maybe that wasn't the best idea ever. So.
Their sort implementation was 17 times slower
That's
What was the reasoning for it? Well, I think it's the.
Because everything was like Rust,
so that's why like.
Oh, there's probably optimization that
We're writing on Rust.
Oh, no doubt, no
Right.
doubt, but that was the point. was
The
that
first
they've
time,
already-
the first time they do it.
Yeah, but seeing as
I think
one
that's-
fine-tuned
No,
control.
that's-
Well, we can chat after, we're running a
That's
little.
what people are always saying, they don't give a reason, they just say, well, we
Just,
write on Rust.
Oh, no,
There's
it's
no
just.
reason, that's what they always say.
So, yeah, to wrap up here,
You don't listen to mono language.
Exactly.
Yeah, to wrap up here,
Yeah.
Paxos shows that distributed consensus is
Yeah.
possible.
And if you need hardware control, see.
Oh, yeah, that was my first language.
You know, assuming we're not talking about, you know,
Yeah.
Byzantine failures, but Paxos shows us that distributed consensus is possible in a realistic way, in the sense of realistic with, you know, a toy collection of servers and stuff that would never be acceptable at a real company, but no, but like in a realistic, like, it's not an algorithm that's so hard or requires like exotic hardware or something like that. Like, this is a real thing that you can do. And TLA Plus shows us that we can use, you know, that we can come up with practical implementations of these things. Most of the multi-Paxos implementations have TLA Plus implementations that you can go play with, see what the benefits are and everything. Yeah.
Are there any multi-Paxos implementations that, or my understanding is multi-Paxos is when they modify the assumption set essentially, or is there extensions on top of regular Paxos?
Yeah, yeah, they're basically, they are versions of Paxos that can be used in multiple times
So,
with various other assumptions to make that
are
possible.
there any assumptions where it's like you can have a malformed packet, or you can have a
Byzantine,
yeah,
yeah,
so
Byzantine
are-
versions of Paxos.
Oh,
yeah.
there are Byzantine versions?
I think so, yeah. I think there are I think so.
Or do you just wrap every single message and or append the CRC every single message or whatever?
That's probably what
Yeah,
check
I don't remember. Yeah, I thought there were variants of multi-Paxos that were Byzantine.
I mean, because if you can encode the message and encrypt it, if the message doesn't arrive, it's a network failure.
Yeah.
Yeah. So yeah, we are running a little bit tight on time, but thanks everybody. Yeah, what's up?
Is there a minimum number of actors or nodes? Is it like
Yes,
three, or-
you don't wanna do Paxos with less than 6. And the Paxos is one of those algorithms, when we say usually distributed algorithms, you wanna have an odd number. A lot of times that's because we're pointing to things like Paxos.
Wait, so would it actually work with like 2, or would it like?
Yeah, parking tag, stuff up here, again,
Well, you
it doesn't make it free, but it makes it a lot
You can't
cheaper.
ensure the
Right, yeah, that's fair. But that's why I was curious if you can actually do
Yeah,
it.
that's why he said always it all.
Nice seeing you again. Ah, hey, it's the guy, right? From Rackspace. But I think like you told me you were switched from Ice to Rackspace?
No, not for a long time.
Yeah.
No, I'm in startups.
Oh, you're in startup.
Where have you been? Actually, a database company, and we use Graph like, for the database.
Oh, which database?
Events one. No, I'm at another company, and I'm working on, well, both, you better be tuning up for this.
Okay.
Okay, but, it's for legal tech. Anyway.
So it's not your startup, is it? Oh, good for you.
Well, I mean, it's,
Could have been saying maniac startup.
I don't know. It's almost, it may be almost a workforce startup.
Like 6 signers.
Yeah, it might be a potential workforce startup right now. It's like one of the 3 or 4 companies that are gonna have left to handle all this. You know,
The actual AI knowledge, yeah, but I feel like the real, like a lot of the reports are more like creating applications of AI.
oh yeah.
Like there's gonna be like, there's going to be like 2 or 3 like AI modeling companies. But there's gonna be a lot more money in like, I have this AI to help with oil or something.
Yeah.
Yeah.
Yeah, it's definitely interesting. I feel like I need to learn more about AI in general, though, because normally, once it's done, ideally, it's just kind of like, oh gosh. Testing, 1, 2, 3.
Oh shit, so you already like transformer?
No, I just wanna,
You guys are keep clean.
Yeah, at this point, I eventually do need to go shopping.
no, I was,
Maybe instead of fucking it,
I was presenting
I'll make a mess of that little attic space.
Yeah, it's a lot of work, and I like the complexity.
Oh, really? Okay. Well, that's like,
Yeah, like I use Rust, there's a lot to go. You want to build like really faster.
Yeah.
I don't know, it's still
Yeah, I mean,
I speak to the folks that
I think
represent
it was kind of a frustrating one.
Okay, yeah.
It's fast and it builds with relatively small binary.
Okay, cool. Yeah, yeah. Oh, yeah. There's absolutely like a lot of overlap.
It's too simple. It's like, I mean, it's like, the only problem is that's like everybody. That's true. There's a lot of stuff. There's a lot of stuff. Like probably it's kind of funny. I don't know Cambridge, but
Well, once you know, we're even more off. I'm in the North Sea. You have to reach this guy over a telegram. I was signal to the. Oh, Norway? We're talking about even more hard.
Oh, that's like hard. Yeah, yeah. And we've got, Professor Hunt just said that he'd be willing to
hang out.
speak there when he's got time.
Do you see the
Right
list
now
of
it's
announcements
like,
stuff? Do you follow the?
right now,
You can check out usandlesswrong.com and it's all the calendar of all the events. I bring it up because 2 days, Petra, like the Unitied Less Wrong celebration. That's South Austin off of Williams Street. That's at Kyle's house.
Oh, cool. Okay, yeah.
Yes.
Yeah,
Oh, yeah.
ceremony and whatnot.
Well, and GCHQ
alcohol
and
and
stuff that.
cooking use in the bathroom.
Oh, right, that's very good. Thanks.
Yeah, yeah.
Let's run that on.
Stickers if you want them.
I'm Constantine.
Constantine.
Yeah. I'm Graham. Nice to meet you, Graham. And what do you do? Oh, you're ambassador.
I used to work for R.
Dive into it.
Okay. Oh, so Cherry, I thought, so what does Cherry stand for?
Capability, hardware, enhanced risk instruction sets.
Oh, wait, so is it the same as like RISC-V or RISC-V or whatever?
Well, RISC-V is a microarchitecture, but Cherry is an extension of that microarchitecture.
Oh, okay, got it. Oh, so
it's memory
so
tagging,
that is
so
one of the
you have to know point.
right.
There are
So
areas
it's basically
where
a capability, we're
that
replacing
gets into the gray
pointers,
area.
and
Does
then
that
we call them
count as business?
capabilities, because they're more like
Because
the way that you
choosing
handle.
to, oh, I didn't see that packet because it
If
wasn't
you
the one
want
that I
to
wanted.
specifically talk to a file in the
Violates
Linux system,
the assumptions that
you're giving it
Paxos
capabilities
So
and
it
permissions that have a
violates
certain
the
fine
guarantees
grained
that Paxos
access
is
control
making.
on that
But it
memory.
doesn't necessarily get you
So,
into a bad
in effect, what it gives you, it gives you
Like,
compartmentalization.
maybe the state that
For
you
your
do get
program
into,
space,
what emerges from
you have
that
to do a
is
little bit of
something
work
that's
up front to
But
compartmentalize your
that's
data,
outside
so
of the
you
scope
do
of
get
the assumptions of Paxos.
infiltrated
And
or
so
whatever.
what you're describing is
allows,
absolutely one of the
glassability
areas
to be
where a lot of that kind of research
Okay.
has gone.
It minimizes collateral
Right.
damage.
But
You
that
have to do a
wouldn't
little
be
bit more
Paxos anymore if
formal
you were
methods
doing
up
that.
front
With Paxos,
to
the
kind
whole
of
point
secure
is
your, that's why,
that we
you know,
come to a
secure military applications.
It's more
are
important
first
that we
and
come to
foremost
one than it is
infrastructure,
what
which
it
is
comes
my
to
interest.
now. But if
critical
you care
infrastructure.
about what the
But
consensus
really,
was
it
about,
can,
then
that attack
that's-
surface can,
now you're getting
start to
into
narrow it down.
And that's where a
by
lot of people,
constructing the code.
when they give the examples of Paxos, sometimes they shy away.
So you're based in
from
Austin, or where are you
using
based?
like,
Okay.
you know,
I've been there
Oh,
for
cool.
25 years.
They're like,
Oh, okay,
server one is.
I-
The accent hasn't gone
Because
left
we
me yet.
genuinely don't
Okay.
get server
Code
one,
running and all that.
fine.
I
No